Greetings everyone, I hope you can hear me well. My name is Guilherme, I'm from the University of Campinas, Brazil, and today I'll be presenting my work entitled Estimation of Protein Topological Properties from Single Sequences using a highly parallelized minified language model. As we all know, artificial intelligence was responsible for great revolutions in protein structure prediction, to a point where secondary structures and other one-dimensional properties can be predicted from primary sequences alone without the need of multiple sequence alignments. However, the algorithms behind those predictors are growing in size and complexity, and right now their requirements are larger than ever. Motivated by this, we set a goal of building a property estimator that instead of going bigger and better, could go smaller and faster and deliver the same performance. In order to do so, we studied some modern predictors and, inspired by them, set some design principles for our work. First, we committed to deep neural networks with scalable parallel operations, and understanding that sequence-to-sequence architectures were part of our core, we avoided recurrent neural networks by design. We wanted our model to be inclusive and democratic, so it was made to be 100% open source, open data, and implementable on consumer-grade computers. And finally, we implemented our model with the Julia language, a rising language for scientific computing with an ever-expanding machine learning environment. Our network, called Tintinet.jl, is a classifier regressor pair, where each component combines embeddings, convolutions, and transformers on an encoder-decoder network, which produces same length outputs for each input sequence. We built a custom modified inception layer to make up the convolutional encoder, which is responsible for processing local information, and included a bidirectional transformer encoder to further process the sequence, including global information. Finally, convolutional detection heads are responsible for the output generation. For the input data, we chose the COTH-S40 database as our main source of samples and extracted the output properties using the SSB. After parsing and aligning the outputs, we fed those input-output pairs into the network on batches of 138 sequences, with 10-fold cross-validation. For each validation fold, training was performed on almost 30,000 sequences. We adjusted the maximum sequence length and batch size to make the training procedure fit on an NVIDIA GTX 1650 GPU with only 4 GB of memory. We evaluated Tintinet.jl side by side with the same single sequence property estimators we used as inspiration, and compared some figures of merit on the same validation set. For classification, Tintinet.jl ranked first place on the relevant metrics, which are the prediction accuracy and free-state segment overlap score. For regression, Tintinet.jl ranked second out of the 4 models evaluated on the relevant metrics, which are circular mean absolute errors for phi and psi angles and regular mean absolute error for the solvent accessibility. We do note that in case of regression, the top-ranking model is an ensemble of networks with almost 100 times more parameters than Tintinet.jl, so we remark that we got to be competitive with only a small fraction of the total network size. We also benchmarked execution times for a model, again comparing them with 3 other methods with independent incremental sample sets of same average length. And as expected, due to a combination of a small parameter pool and the application of our design principles, we were happy to notice that Tintinet.jl was the fastest model to generate a prediction per sequence in average. It was also 10 times faster than the model ranked first place in the regression task. In conclusion, given this proof of concept task, which was building a portable, language-based, one-dimensional property estimator that could deliver competitive predictive performance and execution time, our model ranks between first and second place on the selected key performance indicators. Tintinet.jl is available on GitHub, and I've added a link QR code to the repository. I'd like to thank our financing agencies in Brazil, CAP, CNPq, and FAPESP, as well as the Institute of Chemistry and Center for Computing and Engineering Sciences. Thank you very much for your attention, and I'll gladly answer any questions you have.